Hey, good morning, everybody. This is Mr. Ainsworth, and we are going to go through Chapter 9, Sections 1 and 2 review. Get your calculator handy because we are going to go through all kinds of Fibonacci work and with recursive functions, the whole bit. So have your calculator ready. I'm going to be using the TID4 here. You can use whatever you want, and let's get started, okay? And remember, this is a video, so you can pause and play and go through any portion of the video you want over and over again if you need to. Or you can advance it and watch different parts of this if you only need to see a certain problem. So keep in mind that this is a video. It can be paused and played, rewinded, fast forward, you name it. So use it to your advantage. All right, so the first thing we got to do is list the first 15 Fibonacci numbers, starting with the two seeds. Okay, those are the two starting numbers right here. We add them. All right, 1 and 1 make 2. 1 and 2, 1 plus 2 is 3. 2 and 3 is 5. 3 and 5 is 8. 5 and 8 is 13. 8 and 13, 21. Keep adding. You get 34, 55. The 11th Fibonacci number is 89 because 34 and 55 is 89. 55 and 89 is 144. And then you get 133. And then 377. 610, and then you add these two and you get 987. So 987 would be the 16th Fibonacci number. Okay, so first 16 Fibonacci numbers. Okay, I added the 16th in there. Okay, so there we go. There's the first 16. Now let's work with them here and throughout the exercises. All right, so and this first one here doesn't have anything to do with Fibonacci numbers, but we want to, given the recursive relation right here, the recursive function relation, and the seed, that's your starting term. Okay, that's your starting term. Show how to find the next three terms. All right, so here we go. All right, so what this is saying is that we have a sub n is always equal to 7 times something minus 2, where this a sub n minus 1 is your previous term, okay? Well, that means a2 is equal to 7 times the previous term, a1, minus 2. So that means we got to take 7 times 2, which is my previous term to a1, and then minus 2. 14 minus 2 is 12. a2 is 7 times the previous one, which is 12, minus 2. 7 times 12, 84, minus 2, 82. If you don't believe me, just enter it in. So you go 7 times 12, all right, minus 2, and that's, well, you got to enter it in correctly here, so let me try that again. I didn't do it correctly here. 7 times 12, that's 84, all right, minus 2, it's 82. And we got to take 7 times 82 minus 2. So you got to substitute that in. You always take the previous term and substitute it in. So you got to take 7 times that. So 7 times 82, all right, minus 2, 572. So you always take the previous term, see, right here. Take that previous term, substitute it in. Then take the previous term, substitute it in. All right, you always, that n minus 1, this right here, this means previous term. Previous to a sub n. Previous term. This one, this recursive relation means take the two previous terms and add them together. All right, sum the previous or add the previous two terms. So I'm going to write that down in English because that's what it means. A sub n minus 1 and a sub n minus 2 are the two previous terms to a sub n. So add the previous, keyword previous now, all right, two terms. That's what that means. So a2, or a3, excuse me, is a1 plus a2. So 3 plus 7, well, that's 10. a3 is the sum of a2 and a3, so it's 7 plus 10. That's 17. And then I've got to take 7, 10, and 17 and add them together. So a5 is a3 and a4. So 10 plus 17, well, that's 27. All right. 3 plus 7 is 10. 7 plus 10 is 17. 10 plus 17 is 27, and so on. Add the previous two terms. Add. Okay. Next one here. We've got to simplify without a calculator. So we're going to use the famous phi to the nth power formula here. So phi, your golden ratio. Remember phi. Oops, not that one there. Phi all right, is that golden ratio. Golden ratio. And phi, I'll just write it down over here, phi is equal to 1 plus the square root of 5 divided by 2, or 1.618 as an approximate number. So we're going to take that to the 16th power, and this is how we do it. We're going to take, this is f sub n times phi, so f sub 16, all right, times phi, plus the previous one, f sub 15. Okay, this is the previous Fibonacci number. Previous Fibonacci number. All right, previous to the 16th term is the 15th term, right? All right, so let's get started. Okay, so we need the 16th Fibonacci number. So we go back up here, and we understand that it's 987. So 987 times 1 plus root 5 divided by 2 plus the previous Fibonacci of 610. All right, so a couple different ways to do this, but one way is to take a half of 987 before you distribute. So I'm going to enter that in. So I take 987 divided by 2. I get 493.5. So I'm going to write that down. 493.5, and I got to distribute that through. So what do I get? I get 493.5 times 1, which is 493.5, plus 493.5 times root 5, plus this 610. So I got to add the like terms, which are these two. So I have to add 610 to it. So it's already on your calculator, so just add 610. And I get a 1103.5. So what do I get? 1103.5 plus this 493.5 root 5. And that's the simplified answer for phi to the 16th power. That's a whole lot easier than taking this fraction right here and multiplying it by itself 16 times, okay? Let me tell you, okay? If you had to do this, 1 plus square root of 5 divided by 2 to the 16th power, oh my God, this is hard, okay? That's hard. So you do it the easy way, okay? This is easy. All right, so now we want to take phi to the 30th power, 35th power, and you say, oh, okay, Ainsworth, that's way too hard because I don't know the 35th Fibonacci number, okay? So, okay, that's true, I don't either, but we're going to find it. So we're going to take 35th Fibonacci number times phi plus the previous one, that's the 34th Fibonacci number. So we got to find these first, all right, using what's called Benet's formula. And f sub n is equal to, all right, 1 plus the square root of 5 divided by 2 to the nth minus 1 minus the square root of 5 divided by 2 to the nth divided by root 5. All right, there's Benet's formula for the nth Fibonacci number. So I substitute 35 in for the exponent. Let me show you where. Okay, so notice the exponent here. I substitute here and here only. So I got to evaluate 1 plus the square root of 5 divided by 2 to the 35th power minus 1 plus, 1 minus, it's a minus right here, 1 minus the square root of 5 divided by 2 to the, not the nth power, to the 35th power, divided by root 5. I need to do the whole thing on the calculator, and I should end up with this one right here, this big number right here. Let me highlight it. That's my goal. Okay, how do I know that? Well, I got this from the internet, guys. I just went searching and found it. Okay, let's verify it though, because we just don't trust the internet because it may be wrong. There's a lot of things out there that are not correct on the internet, so you got to be careful. Okay, so let's enter this in. I need to do double parentheses because one thing that's important when you use a calculator here is you got to put the numerator in parentheses. So it's a double set of parentheses are needed when you do this whole thing on the calculator. And then you go 1 plus root 5. All right, got to get out of the root, close it off, divide by 2, close it off, take it to the power of 35, get out of the exponent. Now I do the same thing, but I minus, okay? So minus double parentheses, 1 minus the square root of 5. Okay, I got to close it off, divide by 2, close it off, take it to the 35th power again. At this point right here, I got the entire numerator in. All right, I'm going to press enter and then divide it by root 5. So divided by root 5, that's important because you're not done yet. And notice that I get, looks like 9,227,465, which is the same number here. Okay, so let's write that down. So 9,227,465. And this is F35. Okay, F35. And right here, this is F36. So let's get that one too. Let's verify. Excuse me, I don't need F36. I need F34. So let me erase that. The one above it. Okay. Okay. Why? Because it's the previous one. So let me write it out. So let's use Benet's formula first. So it's 1 plus the square root of 5 divided by 2 to the 34th minus 1 minus the square root of 5 divided by 2 to the 34th divided by root 5. You have to divide it by root 5, otherwise you're not going to get the right answer. Okay, so let's see here. Second entry. That brings, I don't want that second. There we go. So notice that if I go second entry right here, I bring up the last expression. So what I want to do is go back to my exponent. I want to change it to 4. You can re-enter this entire thing, but if you're doing what I'm doing right now, it might be a little bit easier. Oh, got to get to the right spot. Okay, so I just changed, whoops, the exponent to 34, then I hit the enter button, then I divide it by root 5, and I should get 5,702,887, which I do. See, right there. Okay, so let's record that. Now that I verified everything, so we've got 5,702,887. All right, so what do we have? So let's simplify this. So here we go. So 5 to the 35th power is the 35th number, which is the one in red here. So 9,227,465 times 1 plus the square root of 5 divided by 2 plus this number here, 5,702,887. Okay, I got to take half here. Okay, so let's see if I have that. Don't have that on my calculator here. So I'm going to enter it in. So 9,227,465 divided by 2. All right, and I get this number here. So let's write that down. 461, 3732. So 461, 3732. Let's see if I did that right. Just double check. 461, 3732.5. Okay, now I got to distribute that through. So I get 4,613,732.5. That's times 1. Now times the root 5, so same thing. Plus this number here, which is 5,702,887. Now what I need to do is add this, the like terms. So let's do that. I already have this in my calculator here. So what I need to do is add the 5 million here. So I go plus 5,702,887, and I get a bigger number, right? So I get over a billion. So let me see. I didn't say that right. So 103,166. So 103,166. I'll say it properly in a minute. 19.5. So 1. Okay, so this makes sense. Okay, so 4 million, 5 million over 10 million. So 10,316,619.5 plus 461,3732.5 root 5. There we go. And that's my final result, guys. Okay, no problem there. Okay, now if you need to rewind that, go ahead. I mean, there's a video, right? So you can pause, play, rewind. You go back and listen to that as many times as you need. Okay, so here, calculator required. So let's enter it in. Here we go. So I'm going to do the step-by-step approach. So 1 plus root 5 and hit enter. Divide by 2, enter. Raise to the 16th power. Okay, there's your numerator. Divided by root 5. Okay, there's the entire thing on the calculator. Now I need to round to the nearest whole number, which is 987. Okay, so let me capture this here because I want you to see it. So one thing cool thing about the computer is that you can do cool stuff like this. All right. All right, so here we go. Here's my first calculation right here. This is the first one. Pretty cool, huh? Now it says round to the nearest whole number. No, 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 no. Let's highlight this, okay? That's 987. So 987. I'm going to use approximately equal to because we're rounding here. Okay, notice, by the way, we've seen this before. It's F16. Okay, it's the 16th Fibonacci number. This is equal to F16. And notice the exponent corresponds to that. Oh, maybe there's a connection here. So let's do it again, okay? Watch this. I'm going to take the same step-by-step approach. So 1 plus the square root of 5. All right, hit enter. Divided by 2. Hit enter. Raise it to the 15th. Hit enter. Now divide it by root 5. Look at that. So let's capture this. So I need to round this one too. Because the directions say so, right? So let me capture this. There we go. Let me just clean things up a little bit. There we go. Oops, didn't mean to do that. Hang on, give me a second here. There we go. All right, so what's going on here? Okay, so we need to round it to the nearest whole number here. So let's highlight this. So 609.9. That gets rounded right here. All right, to 610. So that's 610, approximately equal to 610. And if you go look back up here, check this out. It's the 15th Fibonacci number. So you can use part of Benet's formula here to calculate your Fibonacci numbers too, by the way. The question is why? Okay, so notice this right here. All right. The question is, why does this work? Okay, that's my next question here. So let's do this again. So let's calculate this one here. The whole idea is to do this a few times so you see connections, right? So 1 plus the square root of 5, that's my dog outside, and divide that by 2. Raise it to the power. Whoops, don't want to do that. I want to raise it to the power. 14th power in this case. I want to divide by root 5. Okay, and I get 377.0005. All right, so let me capture this one too so you can see what's going on. Okay, here we go. So right here, we want to round this one here, okay, to 377. So this is approximately equal to 377, which corresponds to, well, let's take a look up here. Oh, the 14th Fibonacci number. Okay, so this is equal to F14. And notice that it corresponds to the exponent. So you can use part of Benet's formula, but you got to round your answer to the nearest whole number. Okay, so one last time, just to hit it home, okay? So here we go. So it's to the 13th power this time. So let's go for it. So we go 1 plus the square root of 5. Just make sure we understand here. Divided by 2. All right, raise it to the 13th power. Divided by square root of 5. All right, you get 232.99. Okay, so let's capture that real quick, and they'll be done with this exercise. Okay, so let me just decrease the size a little bit. Let's bring it over here. There we go. So we want to round this number here. 232.999 is 233. So this is approximately equal to 233, which corresponds, all right, look at this, to the 13th Fibonacci number. So this is equal to F13, 13th Fibonacci number. So I did it 4 times in a row to show you that you only need really part of Benet's formula to calculate these values here. And kind of, if you understand the form here, it gives you the result in advance. So is there any correlation or relationship between the exponent and the result? And the answer is obviously yes, because I've explained it 4 times in a row. All right, explain and be very specific, give mathematical examples to explain. So previously here, these are the mathematical examples. So let's see here. So F, all right, since, all right, F13 is equal to 233, all right, 233. F14 was equal to 377, which is the 14th Fibonacci number here. All right, the exponent, all right, the exponent determines the Fibonacci number you're looking for. The Fibonacci, all right, number you are looking for. All right, so what I'm saying is 1 plus root 5 divided by 2 raised to the nth power divided by root 5 is approximately equal to f sub n. That's what I'm saying. All right, if you round it to the nearest whole number. Okay, so there you go. There's my conclusion right there. All right, so next big question is this. In Benet's formula right here, in Benet's formula, explain why this portion right here, this one, this second portion of the formula, doesn't affect the answer much at all. In fact, it is not necessary to get the Fibonacci number you're looking for if you round it to the nearest whole number, which is what I just did earlier. Why is this? And explain through a mathematical example. So let's do that. So let's calculate F30. So here we go. So F30 is 1 plus the square root of 5 divided by 2. All right, to the 30th power minus 1 minus root 5 divided by 2 to the 30th divided by root 5. So here we go. This is how we explain it. We do this step-by-step approach. So 1 plus the square root of 5. Oh, I didn't mean that. So let's start over. So 1 plus the square root of 5 divided by 2 raised to the 30th. Okay, this is going to be a big number, okay? So let's write it down. So 1860498. So this is 1860498 minus what here? Okay, so my first part of the expression is huge. Let's see what this is. Okay, so let's redo it. 1 minus the square root of 5 divided by 2 raised to the 30th power. Watch what happens. Oh my God, it's super duper small. Okay, this tells me right here. Let me capture this. Let me show you what I'm talking about here. Now I know you can't do this, but you can write it down, okay? I can do this digital stuff just because I got a cool computer. However, you just write the stuff down. Okay. So what am I saying? Let's take this here. So what this means is I got to shift the decimal 7 places left. Shift decimal. All right, 7 places left. All right, this is very, very small. Very small number. All right, in scientific notation, when you end up with a negative exponent, this indicates you have a very small number. This is equal to 0.000000. You've got to have 6 placeholders because you're going to shift it over 7 places, right? So you move it over once and then 6 more times. So 5, 3, 7, 4. You guys, this is very small. Very, very small. All right, and that number's up here. 0.000000. 5374. 5374. This right here, this number that I'm talking about right here, has little effect on the expression. So let's put it in red. Okay, has very little effect. Very little. That's my Great Dane out there barking. So very little effect on the overall answer. And that's why only this part right here, let me go to switch to blue here. This is the important part. Part of Benet's formula. That's why, guys. All right, so that's why you only need to take a look at this divided by root 5, like in the previous exercises, like these 4 exercises right up here, to determine the Fibonacci number, because the second part of Benet's formula ends up being so small as n gets large. So as you go farther on in the sequence, this number gets smaller and smaller and smaller, and it has very little effect, as you can see. You can see it when you do the step-by-step approach, okay? That is why, okay? So one more time, f sub n here is approximately equal to, all right, 1 plus the square root of 5 divided by 2 raised to the nth power divided by root 5. This is really the only part you need, all right? So if you want to use this to determine any Fibonacci number, you can. It's easier, all right? But you got to round it to the nearest whole number. Remember that. Okay, let's go back in time and do some review problems. So let's find the common ratio, r. So r, the common ratio right here, r is equal to a sub 2 divided by a sub 1, the previous one. All right, and then we'll get the recursive rule. So here r is equal to 18 divided by 3 or 6. And that's why you take 3 times 6 to get 18, times 6 to get 108. So let's clear the calculator, and in 108 times 6. That's your next term, 648. All right, times 6. Again, you just go times 6. Easy. 3,888. The recursive rule, any term is equal to the previous one times 6. A sub n minus 1 times 6, or 6 times a sub n minus 1. The order here doesn't matter. Okay, on this one here, the recursive r is, again, a sub 2 divided by a sub 1. So 64 divided by 256. Okay, now if you don't know what that is simplified, all right, you divide both of them by 64. 256 divided by 64. All right, that's 4, right? So we know this is 1/4. Okay, you multiply it by 1/4, so times 1/4. A fourth of 64 is 16. 16 times 1/4 is 4. All right, when you multiply by 4, it's the same thing as divide by 4, right? Dividing by 4 and multiplying by 1/4, which is multiplying by the reciprocal, is the same. And you divide by 4 again, you get 1. So the recursive rule, I know some of you guys want to write it as a sub n minus 1 divided by 4. Okay, that's fine. But it's really 1/4 times a sub n minus 1. Remember, in general, it's a sub n. In fact, let's put it in red here. For geometric sequences like these, a sub n is equal to r times a sub n minus 1. That's for geometric sequences. Okay? All right, for arithmetic sequences, it's different. All right, a sub n is equal to a sub n minus 1 plus the common difference. So let's see, these are arithmetic. Let's see if they are. All right, so let's see, 42, d is equal to a2 minus a1. All right, so 42 minus 25. All right, so d is 17. So you add 17, add 17, add 17. Okay, each time add 17. So let's check. So 59 plus 17. Okay, you get the next term, 76 plus 17 plus 17. You just keep on doing this, right? So you get 76, 93, 110. So 93 and 110, you add 17. The recursive rule then becomes, all right, a sub n is equal to the previous one plus 17. Look at that, plus the common difference. Now here, it's getting smaller, right? So you're subtracting something. So 13 minus 25, 13 minus 25, that's a negative 12. So you're subtracting 12. So you got to subtract 12 again, right? So negative 11. Let me clear this. So negative 11, all right, minus 12 gives you negative 23. Then you subtract 12 again, right? So you just go minus 12, boom. Even if you didn't know how to add, you could still do it by using the calculator effectively. Okay, you get negative 35. So your recursive rule looks like a sub n is equal to a sub n minus 1 minus 12. Why? Because you're subtracting 12 every time. Okay, quadratic formula time. Okay, here we go. Remember, if I'm going too fast, pause and play. Rewind it if you have to. All right, it's a video, guys. All right, so here we go. Got to set equal to 0 first. Oops, getting crazy there. All right, I don't know how to spell. Ooh, that is my Great Dane talking again. Okay, so let's subtract 1 and let's set equal to 0. X squared is equal, excuse me, not equal to, minus x minus 1 is equal to 0. A is 1, B is negative 1, C is negative 1. So A is 1, B is negative 1, C is negative 1. And I want to substitute them in the formula here. So x is equal to the opposite of negative 1. This means opposite. All right, so the opposite of negative 1 plus or minus the square root of b squared, negative 1 squared, minus 4 times a times c divided by 2 times 1. Now I see double negatives here, and I see them here. So what do we get? 1 plus or minus the square root of negative 1 squared, or negative 1 times negative 1, which is 1, plus, not minus, 4 times 1 times 1, which is 4, all divided by 2. So this is equal to 1 plus or minus the square root of 5 divided by 2. That's my first one. Now on this one here, we're going to do the same thing. We're going to get x squared minus 2x minus 1 equals 0. This time, a equals 1. So this is a, and that's b, and that's c. B is equal to negative 2. C is equal to negative 1. So keep that in mind. So x is equal to opposite of negative 2, which is 2, plus or minus the square root of negative 2 squared, which is 4, minus 4 times a times c divided by 2 times 1, which is 2. Did a little bit of mental math on that one. So I get 2 plus or minus the square root. I see a double negative here. So 4 plus 4 is 8, so square root of 8. All right, just simplifying in my head, divided by 2. Okay, really important here. You got to simplify root first. Okay, now root 8 is root 4. Oops, root 4, sorry. Times root 2, which is 2 rad 2. So this is equal to 2 plus or minus 2 root 2, all divided by 2. And so my final result, if you divide them all, these by 2 here, is 1 plus or minus the square root of 2. Okay. Now, like I said, this is a video, so you can rewind this if you like, okay? But that's how it's done, my friends. Okay, now proportions, solving by cross multiplying. All right, so we're talking this product is equal to that product right there. Okay, so 5x is equal to 4 times 8, 32. After you divide by 5, x is equal to, let me see, 32 divided by 5, divide 6 times, remainder 2. So 6 and 2/5. Okay, hang on for a second. Bring this up a little bit. There we go. Once you wish you can do that on your paper. Okay, next one. All right, 27 equals x times x. Now, x times x is x squared, and that's 27. You got to square root these guys. The inverse of squaring is square rooting. So x is equal to plus or minus root 27, but that's plus or minus the square root of 9 times the square root of 3. So x is equal to plus or minus 3 rad 3. All right, two solutions here. All right, same thing here. We got x squared is equal to 64. So x squared equals 64. That means x is equal to plus or minus 8. Why is that? Well, if you square root 64, you get 8, right? But you got two solutions, okay? 8 squared is 64 and negative 8 squared is 64. So keep that in mind, okay? You got to be careful on this one here. So I'm going to step this one out. X times the quantity x minus 3 is equal to 1 times 4 or 4. Distributing twice, I get x squared minus 3x, not 3, but 3x, is equal to 4. I got to set it equal to 0. So a is 1, b is negative 3, and c is negative 4. So x is equal to opposite of negative 3, which is 3, plus or minus negative 3 squared is 9, minus 4 times a times c divided by 2 times 1, or 2. So you get 3 plus or minus the square root. Okay, look right here, double negative again. So 9 plus 16, 25. So the square root of 25 divided by 2. So that's equal to 3 plus or minus 5. Got to simplify the root, divided by 2. Okay, so 3 plus 5 divided by 2 is equal to 8 divided by 2, or 4. So that's one solution. Next solution. Let me see, where can I put it? Right here, I guess. 3 minus 5 divided by 2 is negative 2 divided by 2, or negative 1. So my two results are right here. All right, they're 4 and negative 1. Okay, we're rocking, we're rolling. All right, last few problems here. So let's do this. We've got some Fibonacci values. We've got to get the 4th and the 7th. Okay, so this is not the 4. Come on, Ainsworth. 4th Fibonacci number. So let's go back up to the top. All right, that's 3. And the 7th is 13. So 3 and 17. So let's here. So 3 minus 9 times 13. All right, you have to substitute in first. So the 4th one is 3. And then F7, well, that's 13. So that equals 3 minus 9, whoops, got to put the right numbers in, times 13. That's negative 114. This is negative 7 times F9, so the 9th one. So that's 34. So 34, okay, negative 7 times 34, negative 238. And this is F15, so what's F15? 610. So this is 610 squared. That's big. Okay, so let's square that. You get 372,100. F9 to the 3rd power. F9 is 34. So this is 34 cubed. That's big too. So 34 to the 3rd power. All right, 39,304. What was that again? Let me see. 393,004. I didn't say that right. Come on, Ainsworth. 39,304. Ah, ha, ha. There you go. You got to say it right. Okay. Number 11. Okay, so how do we do this? So the middle number here. What's 16th and what's 18th? So what's the 16th? Let's go up to the top here. So we got to add these together. So 16th, 17th. So the 17th is 610 plus 987. So 610 plus 987. So let's get that value. So 610 plus 987. So plus 987. What do we have? So 1597. 1597. So this is 1597. All right, so F9. What's F9? So F9, notice it's 34. All right, 144. 34 and 144. So 34, this is 34, and this is 144. So this is F10, all right, and this is F11. So what do we do? What do we do? Well, we could look at the list. We could do that, but let's figure this out first, okay? So notice, I want you to notice something here first. All right, I'm going to write out the Fibonacci sequence. Notice if we know these two terms and we're trying to find this one here, what we can do is we could take 8 and 2 and subtract to get 6, and then take 6 divided by 2 to get 3. So we can subtract the two terms and then divide by 2. All right, it works all the time. So let's suppose if we know these two, look at this right here. If you know those two, you can take 13 minus 3, which is 10, and take half of 10, which is 5, and you get this one. So you can subtract and divide by 2 if you don't know two terms in the middle. So likewise here, I can take 144 and subtract 34. So let's do this. So 144 minus 34, right, divided by 2, and I get 55. Notice that's F10. Let's figure that out. Let's go verify that. So F10 is 55, see? So if you don't know two terms in the middle, you could subtract the two that you know and then divide by 2. Let me write that out. Subtract and then divide, all right, oops, sorry, divide by 2. Okay, so subtract first and then divide by 2. So 144 minus 34, all right, that's 110, divided by 2 is 55. So this is 110. 110 divided by 2 is 55, and that number goes here. And then 34 plus 55, well, that's F11, right? And that's 89, okay? And then you just add the previous two to get to the next one. So on this one here, we got to take these big numbers here, because you don't know where they are. You got to subtract them and divide by 2 to get to the second term in this part of the sequence of Fibonacci numbers here. We know they're Fibonacci numbers. So what we need to do is enter this in. So let me clear it out. So 165, 58, 01, 41. Let's double check. Got to make sure you entered in correctly. That's one of the toughest parts too. All these big number problems here. We got to subtract this other number here. So minus 39088,169, and you double check it. Make sure that the number's entered correctly here. So 39088,169. Okay. Now we got to divide it by 2. Okay, so that number goes in the middle. So 632,459. 632,459. 86. 86. Now we take these and we add these two together to get the next one. So now we add these two because they're Fibonacci numbers. That's what you do to get to the next term. Now we already have the second term in the sequence, so we just add the first term. So we add, all right, the 39088,169. And we get the next term. So let's write that down. 102334. 102334. Let me bring it back. 102334, 155. It's a big number. Now to double check, we can add the red and blue numbers and we should end up with the final. That's how we check to see if we're right. So let me add the one in red. So plus 63245986 and hit enter. And do we have this last digit? Yes, we do. We have the last one. Okay, so it looks like a lot of work, but it's really not. So let me bring this in. Okay, and that is how we did that one right there. So, okay, now let's finish up here. So we can do the last one too, same way. All right, so let's figure this out. Let's clear this out. We're going to have to enter this big, huge number in here. So 203,650,11,074 minus the first one, 125,862,69025. Hopefully that's, now we double check at the end, okay? All right, so Here we go. So let's write that down. So we have 777,874. 777,874, 2049. So 2049. Now we add these two to get the next term. So I add 125, 862, 69025. That'll give me the next term, which is huge. Let's see here. Just seeing if I can change the mode to get more digits, because it's hard to see all these digits here. I got to shift this over 10 places. 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't know the last digit. Some calculators show more than 9 digits, this or more than 10 digits, and this one doesn't. Okay. So we don't know the. Let me see. So let me write this down. So 20365. So 2 0. What was that again? 2036501. 2036501. 107. 107 something. All right. The reason why I say something is because I don't know the last digit. I'd actually have to add these by hand, so the last digit has to end in a 4, I think. So, no, let's see. Yeah, boom, boom, 5 and 4. I think so. Ends in a 4. Something must be wrong though, because that can't be right. I'll have to double check this one. Let me check this one later. Okay. What was Leonardo Fibonacci's real name? You got to research that, guys. So check this out. You got to go on the internet and research what was Leonardo's Fibonacci's last name. I'll tell you what, I'm going to hold off on that one because I don't feel like going to the internet right at the moment. I'm going to just finish up the mathematical portion, okay? So let me finish this up. So this right here, this tells me, by looking at these are Benet's formula here. This is Benet's formula. So all we really have to do is look at the exponents here to figure out what's going on. And then you see what I'm talking about here. So let's take a look at the first one here. So this is F18. And do we have F18? Sure we do. So F18 is equal to 597 plus 987. So 987 plus, all right, 1597. So, okay, so 2584. So 2584, or you could use Benet's formula. You could do that. Okay, so this is 2584. You can verify that. This is F20. And that's the next one. This is F38. We better just use Benet's formula here. So I'm going to, on the 20th one, I'm going to compute it. It's easier, actually, I think. So 1 plus the square root of 5. Okay, enter, divided by 2. Enter, take it to the 20th power. Enter, divided by root 5. I'm going to just use part of it. I'm going to round it. So 67, 65. So 67, 65. F38. So 1 plus the square root of 5. Enter, divided by 2. Enter. Raise it to the 38th power. Enter. Divided by root 5. All right, and I get this big number here, so 39088. 39088. 39088 169. So 169. So 39,088,169. Okay, so there you go. Use Benet's formula. Use the calculator here. It says use your calculator. All right, and that is it. The only thing you need to do and figure out is what was Leonardo's real name? The real name, okay? Because Fibonacci was his nickname. So this right here, Fibonacci, this is a nickname. I didn't tell you that, but it was. It's a nickname. So what is his real name, guys? Leonardo what? Leonardo. What's his real name? Figure that out, and I'll talk to you later. All right, just go on the internet, guys. It's everywhere. You can figure that out. All right, this is Mr. Ainsworth. All right, remember there's a video. You could go back and you can review anything you like. You can rewind. You can go back to any portion you like. And the key is doing it right and practice. All right, and I'll see you in my next lesson. All right, I'm Fibonacci out of here. I'm done with Fibonacci numbers today. I'll see you. Bye bye.